Hi, everybody. This is again a review for section 1.7, exponential functions. So an exponential growth or decay function, it's a function that grows or shrinks at a constant percent growth rate or shrinkage rate. Uh, the equation is written in the form f of x is equal to a times 1 plus r to the t power. So that t is an exponent. That's why we call it an exponential function. Sometimes you write f of x is a times b to the x, where b is just 1 plus r. What do all these a's and r's and d's all stand for? So the a is the initial starting value of the function. R is the percent of the growth or decay rate, written as a decimal, and b is the growth factor or the growth factor, the growth multiplier. Since powers of negative numbers behave strangely, we limit b to positive values. Let's look at an example of this. I'm going to magically mix. Watch, I'm going to magically make something appear. Boing! There it is. So India's population was 1.14 billion dollars. Oh, people in the year 2008. But that was a nod to the to Dr. Evil, and is growing by about 1.34% each year. Write an exponential function for India's population and use it to predict the population in 2020. So first of all, we're going to start at the year 2008. That's going to be our, how do I say this? That's going to be our 0 year, and we're going to set t equal to 0 in 2008. But let me just switch cameras and show you more whatever. Hold on a second. I'm just going to switch in cameras right here, and here we go. So here's our function. F of t is equal to a times 1 plus r to the t power. T is a time. So A is the initial population, which we were given as 1.14 billion. R is the percent, but we're going to write that as a decimal, so it's 0.0134. And now T is the time. I'm just going to set T equals, now T equals 0 represents year 2008. And we're going to need that really for part B. Anyway, f of t, here's our function. F of t is equal to 1.14. I'm just going to leave it as 1.14, so this will be in billions, times 1 plus 0.0134 to the t power. Now, we want to know the population in the year 2020. So for the year 2020, so for the year 2020, t is going to equal 12 because 2008, because I'm writing in parentheses here, 2008 plus 12 equals 2020. There you go. So for 2020, it's going to be, so f of, I'm going to write 12. So f of 12 means 12 years after 2008 equals 1.14 times, this is just 1.0134 to the 12th power. And that is approximately 1.337 billion people. And that is again, this is an exponential function. That's how we deal with that. Let's look at another problem. I want to go share my screen again. And let's see. I want to put the right camera on. Let's go to another. Let's put in another example here. Oops! Oh, what just happened? Why did this happen? So annoying. Let me just. Okay, let's look at another example. It's going to magically appear. Boing. A certificate of deposit is a type of savings account offered by banks, typically offering a higher interest rate in return for a fixed length of time you will leave the money invested. If a bank offers a 24-month CD with an annual interest rate of 1.2% compounded monthly, how much will a $1,000 investment grow to over those 24 months? So this is a problem of great interest. I see what I did there. Interest because it's anyway. Um, so let's work this out here. So I'm going to again. I'm going to switch cameras here. Let me just jot down some numbers here. Um, so it's 2 years, it's compounded monthly. Okay. So it's 2 years monthly, and and you're starting with how much you starting with here? $1,000. So basically putting down $1,000 for 2 years, compounded monthly, 1.2% interest. Okay, let's see how much money you're gonna have after 24 months. So let's see. Okay, I'm going to switch cameras now, and then we're going. So basically, as I was writing down, you're plugging down $1,000 for 2 years at 1.2% interest compounded monthly. Now, there is a formula which you have learned in compounded. Again, I'm treating this all like it's a review. I'm not actually teaching a whole course in this right now. This is really an algebra. This is algebra. I keep on saying that. When we get to when we get to chapter 2, you'll see there I'll actually start teaching stuff because that's new. You know, it's new material for the course calculus. Anyways, the formula is f of t is a function of time is equal to a times 1 plus r over n. I'm going to explain all these letters here to the nt. So a is equal to the principal. That's the initial amount. Principal. Hope I spelled that right. Uh, and R is the annual interest rate. And N is the number of compoundings per year. And T is the number of years. T is the number of years. Okay. So f of t, and f of t is because that's how much money you're going to have. So f of t is equal to a, which in this case is 1,000, times 1 plus, now the interest is 1.2%. As a decimal, that's 0.012 divided by n. N is the number of compoundings per year. Now we said it's monthly compoundings, so that's 12 compoundings per year, times n, the same n which you already said is, so times t is the number of years, and that's 2 years. So f of t is equal to 1,000 times, how do you like that? 1.001 to the 24th power. And that's going to be approximately $1,024. Actually, I could probably maybe work that on my calculator. Play to the penny. One, and 28 cents. And 28 cents. There we go. So that's oops, there it is. So that's there we go. So it's you got roughly $1,000. Now that doesn't seem like a tremendous amount. You spend 2 years and all you get is $24, but the truth is 1% interest is a pretty low interest rate, and so it's it's not bad. Now, by the way, it's the compounding makes it more. If it wasn't compounded monthly, you would if you just got 1.2 a year, you would have less money. Anyway, that's simple interest. Anyways, what would it be if you had 1.2 per year? 1.2 per year. So it's interesting. 1.2 per year. Okay. Anyways, let's move on. Okay, here's a new problem. Uh, there you go. Bismuth, you like the way I magically make them appear. Example three, bismuth, I don't know how to pronounce it. 210 is an isotope that radioactively decays by about 13% each day, meaning 13% of the remaining bismuth 210 transforms into another atom, polonium 210 in this case, uh, each day. If you begin with 100 milligrams of bismuth 210, how much remains after 1 week? How much remains after 1 week? So, so first we need to establish the equation, and then next thing we're going to do is going to plug in to get the find out how much it's going to be after 1 week. Um, let's see. One thing I always like to tell my students to do in any word problem is to look at all the numbers and see if there are any numbers that are extraneous or not relevant to the problem at hand. And in this example, the number 210 is really not relevant to the problem. It's not relevant to solving the problem at hand. The number 210 may be important for other reasons, but not for the problem that we have to do right now. Because in this case, 210, that's just the name of the isotope. Bismuth 210 is the name of the isotope, and polonium 210 is the name of the transformed atom or whatever. But we're not going to actually we're not you know we again, I'm not saying that the number 210 is unimportant, but I'm saying for us, what we're doing right now, that 210 is not going to be involved in any of our calculations. Anyway, let's get to work on this problem. So let me just jot a couple things down first. Let's see. You begin with so you start with 100 milligrams, and the decay is 13% decay. Um, And I think that's all I need right now. I'm gonna know. Oh, I know 1 week. Okay. Okay, good. We got 1 week. So let me switch cameras here. Stop the share. Switch cameras. Okay, so the initial amount was 100 milligrams. The rate, so the rate of growth, so to speak, is negative 13% because you're you know you're decreasing, not increasing. So that's equal to, of course, negative 0.13. Okay, so Q is the quantity. The quantity as a function of days is equal to the initial amount, which is 100, times 1 minus 0.13 to the d power, to the number of days. It means I multiply this times the number of days, and that's it. That's my formula. Now, the other question is how much left 1 week. 1 week, we're going to say Q of 7, because there are 7 days in a week. And I actually saw an advertisement for a pizza shop, and it said a week, 7 days without pizza makes 1 week. Get it? Equals 100 times 0.87. I just subtracted 1 minus 0.13 to the seventh power. And that is going to be, let me put that in my calculator. say what that's going to be. That's going to be equal to approximately uh, 0.87, raising this to the seventh power, and I get pound, and I'm going to multiply that times 100, so it's 37.725. So there's going to be, so that means after 1 week, you're going to have approximately 37.7 milligrams of this stuff, of this quantity, and that's I was started with 100 milligrams. Now you have less. Why do you have less? Well, it's decaying. That's the whole point. The point is that this is decaying, not. Notice if you have because this is less than one and I raise it to a power, that's why it keeps on shrinking. 0.87, I mean, is less than one. Okay, let's carry on. Okay, I need to switch cameras again, and here we go. Let me share my screen, and here we go. So this principle, now I have to introduce something called Euler's number. Uh, and Euler's number is known as E. It's approximately 2.718282. And so this is something you probably saw this number in algebra, but it's a big number in calculus. Um, and it comes up a lot. Right now, it's going to come up in this algebra review. Uh, but where is it applicable? One of the many places where Euler's number is applicable is in what they call continually compounded, continually. Well, let me just here you go. It's going to magically appear. Boing. Continuous growth. Um, so continuous growth can be calculated using the formula f of x equals a times e to the rx, where a is the starting amount and r is the continuous growth rate. In other words, instead of it's like imagine you have interest. Instead of being compounded monthly, it's compounded daily. Or imagine it's being compounded like every second, teeny bit, you're getting a teeny bit of, and when it comes to growth, it's growing a little bit every second. So so when we do this, we use the number E for this. Instead of, so A is again our starting value, and R is the continuous growth rate. So let's look at a nice little example. Okay, all right. Radon 222 continuous rate of 17.3% per day. How much uh, will 100 milligrams of radon 222 decay to in 3 days? Now it says continuous, so we're going to use the continuous formula. So F of T, or I'm going to say F of D. Actually, I think I'm going to do this by hand. So let me just switch it here a little bit. Hand. So F of D is going to equal to, actually, I forgot the numbers already. So F of D is equal to 100, in this case, times E to the negative, now I have to write this as a decimal, 0.173 D. Now, we want to know how much it's going to be after 3 days. That was the question. So after 3 days, so F of 3 is equal to 100 times E to the negative 0.173 times 3. And that's going to be approximately 59.5 milligrams. So again, this is, and again, it's less than what we started with, But that makes sense because we're it's decay. Now the last thing I want to do is just show you some graph, what the graph of the exponential function looks like. So let's switch now. Let's see what I'm gonna switch cameras. That's the first thing I'm gonna do. I'm gonna switch cameras, and I'm going to share my screen. And here we are in decimal. So let's look at y equal. Now it doesn't matter. I'm going to say y equals. I'm going to say 2. Let's do e. E. Um, Notice when I type in the letter e, Desmos automatically knows 2.71828 and so forth. E to the x power. Okay. So if y, so notice y equals e to the x power looks like that. Let's look at y equals um, 2 to the x power. 2 is a little less than e. So if you notice, they intersect at the point 0, 1. Let's do y equals 3 to the x power. Y equals 3 to the x power. And all three graphs intersect at the point 0, 1. But that makes sense because if x equals 0, y is equal to 3 to the 0 power, which equals 1. Or y is equal to 2 to the 0, because anything to the 0 power equals 1. So it makes sense. I could do 10 to the x. Let's try 10 to the x. Y equals 10 to the x power. And it's going to, again, they're all going to intersect at that point right there. Now the 10, if you notice, the 10 is going to rise more sharply because the bigger number is going to rise faster. If I do, let's say y equals, I'm going to do a crazy one, y equals 1.1 to the x power. And this rises very slowly, but all of them essentially, all of these graphs are basically, all these graphs are asymptotic to the x-axis on the negative side, and then they grow. This is going to grow a lot over as time goes on, but they're all going to go out to infinity. They're not asymptotic, to any kind of straight line like that, but they're all going to grow nicely. Anyway, now what I want to look at next is the difference if I would have. Now we're not going to look at a negative base, but we're going to look at a base that, let's say if the base equals 1. Now if the base equals 1, if y equals 1 to the x power, equals 1 to the x power, then I'm just going to get a straight line. That is just a straight line because 1 to the x power just stays, any power of 1 is just 1. Okay, now let's look what happens if I have not a negative number, but a decimal number. I mean, a number between 0 and 1, let's put it that way. So y equals, let's say, 0.9 to the x power. So now it's good. So that's going to be asymptotic to the x-axis on the positive side. It's going to grow on the negative side. Let's look at y equals y equals. Oh, my picture is as beautiful as my picture is. It's clouding everything up. Let's say 0.5 is 1/2 to the x power. So again, it's just gonna. So when it's so if the base is greater than 1, it's gonna be asymptotic on the left side and it's gonna shoot up on the right side. If the base is less than 1 or between 0 and 1, we're talking about positive bases now. Then it's gonna be asymptotic on the right side. And it's gonna shoot up on the left side. But they're always going to. Now the only way this here is ever going to change. Is if I would multiply the base by I would have, for example, do this. I'll do it this way. Let's say 2. So notice that here, this one green graph is going to intersect at 0, 2, and because of the 2. Because when x equals 0, again, I just y equals 2 times 1. So that number is going to be the y-intercept. the A number is going to wind up being the y-intercept. And that again makes a lot of sense. Well, everybody, has been loads of fun, and we'll see you guys next time. It's been a pure joy.